Hello, Chem class. This is going to be a lesson on how to determine the oxidation numbers of a given compound or ion. And here you should have a sheet that looks like the one that I have here on the background today. And you will be using these rules in a hierarchical order, meaning that if you have something like rule number one will always be more important than rule number two, and rule number two is more important than rule number three. The same thing is going to be true of these different elements, and we'll work some examples so that you can kind of see how things are supposed to work. So our first example here is that we are going to start with an element, and if you see rule number one here, it says that the oxidation number of free elements is always 0. So if I have an example problem like, say, let's start with just the element copper, and I want to know what its oxidation number is. It's just the element copper, so its oxidation number is just a simple 0. If I had a example of an element like a diatomic, like hydrogen, hydrogen is, even though it's bonded to something itself, it's not bonded to another element to make a compound. Therefore, it still follows the first rule, and it also is going to have an oxidation number of 0. As an extreme example, you could have sulfur, which likes to form in clusters of 8, and again, it's not bonded to anything other than itself, and so it also, as a free element, will have an oxidation number of 0. Now that we have the elements down for rule 1, let's move on to rule 2. And rule 2 says the sum of the oxidation numbers in all of the atoms must add up to 0. We're going to temporarily ignore the second part of the rule, and we'll come back to it in just a little bit. That means that we are going to have to use rule 3 in order to help us with rule 2, and these are also in hierarchical order. So let's walk through an example of, we'll start with carbon monoxide. Carbon monoxide, if we look at our list of elements here, neither is an alkali metal, neither is an alkaline earth, neither element is hydrogen, fluorine, or, wait a minute, here we go, oxygen. Oxygen gets to be a -2, so we're going to put a -2 oxidation number there. There's only one oxygen, so the total for the oxygen side is -2. According to our rule 2 here, we just said that it has to add up to 0, the total sum of all of the atoms' oxidation numbers. So that means the carbon side here must be a +2 total, and we only have one carbon, so that one carbon must be representing the whole charge for us of +2, and this is the oxidation number for carbon, and then this is the oxidation number for oxygen. It's not actually the total, it's the individual oxidation numbers for each element. So we now have this finished, carbon with a +2 and oxygen with a -2. Let's do another example. Here we have methane, which is CH4. And as we go through our list here, we see that our third rule here about hydrogen tells us that the hydrogen here is going to be a +1. There are 4 of them, so the total is going to be +4, and knowing this has to add up to 0, our carbon therefore must have a total of -4 for its oxidation values. There's only the one carbon, so that one carbon's value is going to be -4. So these are the oxidation values then for the carbon is a -4 and each hydrogen is a +1. Another example of what we can see with these oxidation numbers shows up if we do something like hydrogen peroxide. So in hydrogen peroxide, we end up going through and seeing that the hydrogen is going to be a +1, and what that gives us for a total then, because there's two hydrogens, is a total of +2. The oxygens must add up to -2, and there are two of them, and so we end up with a value of -1 for each oxygen. In a compound like the following one here, now we have three different elements, and what we're going to do is go through the hierarchy again, and as we go down the list, we find that the first one that we come to that's meaningful to us is oxygen at a -2. So we're going to write the oxygen in at a -2. And that's a total of -2 because there's only one of them there. The chlorine is a halogen, so it applies here on this final rule that I've listed here of being -1. And there are two of them, so that means the total for the chlorine's values is also -2. This thing still has to add up to 0, so in this case this one sulfur must end up being a +4 value in order to make that whole thing balance out to 0. So the sulfur is +4, the oxygen is -2, and the chlorines are each -1 for their oxidation numbers. Next, let's come back to that second part of rule number 2. The sum of an ion equals the charge on the ion. And so if we end up with a material like before, we had copper as an element, and we said that if it's just copper, it has a 0 oxidation number. But let's say that this is a copper with a 2 positive charge on it. Now the oxidation number must also match this value here, so we would say that this has an oxidation number of +2 in order to make this work. Another example of that might be in a compound. You might actually have what's really an ion, and we have maybe PCl4 with a +1 charge. In this case, going through our rules here, we find that chlorine is the only one on the list here in the halogens with a -1. So that means that we have 4 chlorine, so that's a total of -4. But now, when we add this together, it has to equal this +1 here. So let me try a different color there. There you go. And it's going to equal a +1 now. So what does that make our phosphorus? Well, our phosphorus in this case then must end up being a +5 total to make that all add up to +1. So the +5 is the oxidation number of our phosphorus here, and the chlorine is -1. Finally, you might end up with a compound that has maybe a couple of elements that you can't initially find the oxidation numbers for. So let's do an example of something like, say, zinc 2 carbonate. And as I go through the oxidation numbers for this, the only one that shows up on this list here is oxygen at -2. So let's plug that in. And we have 3 of those oxygens, so that's a total of -6. At this point, I don't have any more rules for zinc or for carbon, so I'm going to come down to this rule here. If there are still 2 elements left, solve for polyatomic ions separately. Well, I'm going to put these parentheses in here just to help you visualize what's kind of going on here. This is the carbonate ion, so you would have to look on your polyatomic ion sheet and see that, well, this carbonate actually as an ion has a combined total of -2 for its charge, so I can write that up in into my total here. As I saw for the carbonate. If that's the case for we're focusing just now on the carbonate side of things, then in order for this carbonate to be -2, our one carbon must be a +4. And so this is the oxidation number for the carbon. Once we do that, we can clearly see that this zinc, because this value right here is a -2 for the whole carbonate, the zinc has to end up being a +2 to make this whole thing work. So the final oxidation numbers are zinc for +2, carbon is +4, and oxygen is -2. I hope that this video helped you to understand how to do oxidation number assignments for a variety of different materials. And this is Overlord, over and out.